Welcome to Lecture 2 of the Linear Regression unit. So what I want to do in this unit is I want to talk about the theory behind linear regression. How do we get to these formulas? And so again, if you want to see the details written up with lots of text, you can just click on the link there. So in the last lecture, we talked about what is the best metric to use for error. And we saw that the best one to use is when we're going to use the difference of the squares. This means calculus will be available, and we can use calculus to get nice closed form expressions. So the error, E3, is going to be a function of two unknowns, A and B. So what's a little bit strange here is it's not X and Y that are the variables, which is what we're used to. It's actually A and B. So we're going to consider Xi's the observed data points, and then Yi's the observed functional relationships. So maybe it's a spring and we're trying to see what is the force as a function of displacement. Or maybe we're doing some experiments in gravity and we want to see what is the force of attraction as a function of the distance between two objects. So it's extremely important to remember that X and Y are fixed. They are known, the Xi's and the Yi's. It's the A and the B's that are variable. And we want to find the values of A and B that minimize the area. And the hope is that there should be values, there should be choices that will make the error as small as possible. So in one variable calculus, we had ways to find where a function is largest or smallest. We looked at the boundary points and we looked at the critical points. And the critical points are the places where the derivative vanishes. So multivariable calculus is very similar. You again check the boundary, and now you need all the partial derivatives to vanish and not just the regular derivative. So what does that mean? So this is not a class that requires multivariable calculus as a prerequisite. The goal is to give you a little bit of a sense of what's out there in future classes and what techniques do we need to make this work. So if you've seen multivariable calculus, you can look at this line over here with the gradient, or if not, what dE dA means, this is partial E, partial A, the derivative of E with respect to A. It means we consider all the other variables in E to be fixed. And now E is only going to be a function of just one variable A. So we imagine the value of B is fixed, and for that fixed value of B, we can take its derivative with respect to A using the methods of one variable calculus. And we set that equal to 0. And then similarly, we take the derivative of E with respect to B. So here we would consider A to be fixed, and we set that equal to 0. And so this is going to be the generalization of the critical points. We need each partial derivative to vanish. Now we're lucky, we don't have to worry about the boundary points, because as the absolute value in A and B become very large, the fit is going to become terrible. So we only have to worry about finding the critical points. So if we take the derivative, if we remember what our formula is, well, when the dust settles, we'll get 2yn minus axn plus b, and now we take the derivative of the inside piece, but we're taking the derivative with respect to a. So the derivative will be, the 2 is actually coming from that, will be a negative xn. Similarly, over here, we'll have a 2 and a negative 1. So we now set the partial derivative is equal to 0. We can divide by minus 2, and we get these two sums must be 0. So yn minus axn plus b times xn equals 0. Yn minus axn plus b equals 0. Well, if we look at this, we have two equations and we have two unknowns. What are the unknowns? It's the a and the b here and the a and the b here. So one possibility is we could solve for b in terms of a and then substitute into the second equation. Or if you're comfortable with linear algebra, we could use linear algebra. Either way is fine. So let's rewrite it a little bit cleanly. So if we expand things out and move things over to the other side, we get the sum of xn squared times a plus the sum of xn times b is the sum of xn yn. And for the next one, we'll get the sum of xn times a plus the sum of 1 times b is the sum of yn. So if you're comfortable with matrices, we can put into matrix form as follows. And now we would just take the inverse of this matrix as long as it's invertible. If you're not comfortable with this, what we could do is, well, we could multiply this by whatever we need to cancel for b, or we could solve for b in terms of a and substitute in the other one. There's lots of ways to do the algebra. And so we need the inverse of a matrix. So the inverse of a matrix A is the matrix B, such that AB equals BA equals the identity. So there's a very nice formula for a 2 by 2 matrix. If A is alpha, beta, gamma, delta, we define the determinant to be alpha times delta minus beta times gamma. And the inverse of A is just 1 over the determinant, and it'll be delta minus gamma minus beta alpha. In other words, if you multiply A and A inverse, you get the identity matrix 1, 0, 0, 1. So for example, if we take the matrix 1, 2, 3, 7, it turns out the determinant of the matrix is 1. That's not a coincidence. I wanted to make the algebra nice for myself. I will get A inverse is 7, -2, -3, 1. And you can check and see when you do matrix multiplication that you do get 1, 0, 0, 1. You do get the identity. So we can solve for our point A, B, our best fit values, by taking the inverse of the matrix and then acting on it, having that act on the sum of the xn, yn, and the sum of yn. So all we need to do is make sure that our matrix is invertible. So the determinant of the matrix is going to be upper left times bottom right minus the other two diagonals. And so when the dust settles, if we let x bar is 1 over n times the sum of xn, after you do a little bit of algebra, you'll get that the determinant of n is n squared times 1 over n times the sum of xn minus x bar squared. So the algebra is explained in detail in the packet I referenced earlier. What's nice about this is we want the determinant to be non-zero. We've got the determinant as a sum of squares. The only way that sum of squares can be 0 is if each term is 0. Well, what would it mean for each term to be 0? Well, the only way each term could be 0 is if every data point, xn, is the same as the mean, x bar. So x bar is just the average value. We sum all of our xn's and we divide by n. What would it mean for all the xn's to be the same? Well, it means I want to see how y changes with x, but I'm not changing x. I'm using the same value of x every single time. This is absurd. This is like trying to see how does the, if you have a ball rolling down an inclined plane, I want to see how the time to roll down varies as I change the angle, but I'm not going to change the angle. Or I want to see what is the gravitational attraction between two objects as a function of distance, but I'm always going to keep the distance the same. We should not be able to get any relationship, any fit in a situation like this. And it's great that it breaks down. This indicates that we're doing something right. If I want to see how y varies with x, I've got to let x vary. It's nice that this understands that. So we can rewrite 4 in many different ways. So there's a lot of different ways to do the algebra. I will just leave the slides here, so if you want, you're welcome to look at them or look at the notes. A lot of packages, such as the packages in R and other systems, will solve this for you, and this will just run in the background under the hood. So you won't necessarily see all the equations it's going through. But what's nice is because of calculus, because we can take the derivatives and find the critical points, we actually have closed form expressions. And because we have these closed form expressions, the computer can very easily calculate the answers. If instead we used absolute values, which we saw did give a better fit, it was closer for getting the values of A and B, the problem with that is we can't use calculus, so we have to do a lot more work to find the best values. As the formulas are so important, I'm going to just rewrite them one more time. These are a nice way of writing what A and B is in terms of the sums of 1, xn, yn, and xn times yn, and xn squared. You'll notice the two denominators have a lot in common. And so if you compute one of them, you really know the second. So you can think about how many fundamental objects you need to compute to really determine A and B. And I want to end with just a few brief remarks. So the first is that the formulas for A and B are reasonable. And so, when you see an expression like this is a long expression. There's a lot of terms going on here, a lot of sums. Is this reasonable at the end of the day? You want to think of what kind of tests can I do to make sure this is a reasonable formula? Well, I like to put units in. So let's imagine x is in meters, and let's imagine y is in seconds. So if y equals ax plus b, if y is in seconds and x is in meters, then b would have to be in the same units as y, so b would have to be in seconds, and a would have to be in seconds per meter. And so if you go back to the previous slide, you can go through and put in the units for x's and y's and see that you will get the right thing at the end of the day. So that's a good way to see that the answer is reasonable, this quick unit analysis. And we'll talk a lot more about units later in these series. The last one is, I mentioned that there's many ways to get to the same point. Depending on how you get there, you might write the final answer slightly differently, but it's still going to be an equivalent answer. So if you're not comfortable with matrices, we can do it by isolating for one variable in terms of another. So imagine we have two equations and two unknowns. Maybe when we put in all of our values for the x's and y's, we get 4 equals 3a plus 2b, and 5 equals 2a plus 5b. So we could use the matrices, but we could also solve for b in terms of a. There's many ways to do this. I could say, well, 2b equals 4 minus 3a, so 4 minus 3a divided by 2 equals b. That's one way to do it. But I'm going to have fractions. So another thing I could do is I could multiply the first equation by 5 and the second equation by 2. And when I do that, I'll get 20 equals 15a plus 10b, and 10 equals 4a plus 10b. And now if I subtract, the b terms cancel, and I'll get 10 equals 11a, so a equals 10 elevenths. And from that, now you can easily solve for what b is. So this finishes the second of the lectures on regression. And so what we did today is we saw the theory. We saw how using squares to measure the errors, calculus is available. We find the critical points, we find the places where the derivatives are 0, and that gives us explicit formulas for the best fit values of a and b. And once we have these explicit values, we don't have to go through the derivation anymore, we can just use them. And this is why programs can be, like R can calculate the best fit lines so rapidly. If we used instead absolute values, it would be a tremendous amount of more work.